A still picture of a value stream map may not fully explain the behavior of the value stream. In some cases, we need to understand its dynamic behavior. To do this, we will convert our Excel value stream map into a Monte Carlo simulator. Mapping the current value stream is a good starting point to understand how it behaves, but this instant picture may not be representative of its behavior in the long run. To further analyze the value stream behavior, we need variation data on its critical parameters such as inter-arrival times, process times, first pass yields. Download this Excel Simulator VSM Simulation1.xlsm from OneDrive. In Excel Value Stream Map, we saw how a complex value stream could be mapped using Excel. We saw the importance of mapping feedback loops such as test repair loops because they may become the bottleneck for the complete value stream. In this situation, not all items flow along all branches, so we need to calculate the percent flowing along each branch. This enabled us to calculate the cycle for each workstation based on the staffing. Finally, we were able to calculate the ideal staffing to balance the line, ensure no workstation cycle is above the average inter-arrival time, TAC time. This we did using Solver. We need to measure inter-arrival times and process times for each process step. To do that, we take 10 measurements of each in Gemba and calculate the average and standard deviation. We assume that process times follow a normal distribution, with average in K and standard deviation in L. On the other hand, looking at the inter-arrival times, we notice that the standard deviation is greater than its average and the shape of the distribution is telling us that it is closer to an exponential distribution, so we will use this assumption in our simulation. In this case, the inter-arrival times average in K3 is 5 minutes. We now enter these averages and standard deviations in columns K and L of our simulator. A value stream map is not complete without work in process, WIP, data. The problem with WIP data is that it typically varies widely along time, so a snapshot of the moment we visit the line may be very misleading. In our VSM simulator, WIP before each workstation, column Q, is calculated each hour based on historical data collected. New WIP equals previous WIP plus items processed by previous step minus items processed by this step. Items processed, column R, are calculated each hour based on average time, K, time standard deviation, L, and staffing, M, considering the constraint of having enough WIP in the previous step. Lead time in column T, for each process step, is the average time it takes for an item to be processed in that step, including the waiting time due to the WIP in front of it. Capacity utilization in column U is the average percent time the workstation has been operating since the start of simulation, based on its theoretical capacity. WIP, Q, and capacity utilization, U, are shown on bar charts on the right. Elapsed hours simulated are in B2. Products received for repair, products repaired, and products returned without repair are shown in column A. Total values for columns K to U are shown in row 1. K1 is the average value add time, total process time, per product. M1 is the total staffing in the line, full-time equivalent. T1 is the total lead time, in hours the average lead time as seen by the customer, not including the customer contribution. U1 is the overall line capacity utilization. P1 is the maximum value of all cycle times, it corresponds to the line bottleneck capacity. P1 should be less or equal than K3, TACT. This means that all cycle times must be below TACT, inter-arrival time. Q1 is the total WIP in the line. Products received for repair will still be in the line, WIP, unless they have been returned to the customer, repaired or unrepaired. Received A3 equals WIP Q1 plus repaired A13 plus returned without repair A8. The value add time is the total operator time in K1, 66 minutes. The total lead time is in T1, 23 hours. So, the ratio value add to total time is 4.8%. The rest of the time is waiting times along the total value stream. To run the simulator, press F9 to simulate 1 hour. Keep pressing to run several hours. The counter in B2 shows the elapsed simulator hours. To start simulation with an empty line, press Ctrl key plus R or press the reset button. This will reset all line WIPs to 0. To simulate 100 hours, press the Run 100 button. Unprotect this sheet before using Solver. Do not run with empty yellow cells. In the tab Evolution you can see how all process and WIP values evolve along each hour in the main steps, as well as the evolution of total lead time. During the first hours, when the line is empty, there is no waiting time along the process, so the total lead time is basically equal to the value add time, 1 hour. As queues start building up, as shown in the WIP chart, waiting time starts to increase in all workstations, and that causes the total lead time to increase to a value of 20 hours, where it seems to stabilize. This means that if we take a snapshot of the line in hour 7, total lead time is 8 times value add time. On the other hand, if we look at the line in hour 45, when stability seems to be reached, lead time is 20 times value add time. Non-value add time is made up of all the waiting time taking place in front of each workstation. We can see that, although the average inter-arrival time is 5 minutes, 12 items per hour, 3 arrivals of more than 30 items each have collapsed receiving, causing an accumulation of 100 items in reception, which has eventually been absorbed by the line. This is a typical case where most of the variability comes from the customer inter-arrival times, as seen in the process chart. Tracking this evolution you can discover unexpected bottlenecks, caused by variability, that may need to be reinforced with additional staff. We can also estimate the total lead time we can commit to customers. In this case, if the process is stable, that would be 20 hours minimum. Long lead times seen by the customers are caused, mainly, by variability. Any reduction in process variation will, therefore, reduce WIP and, therefore, lead time. In this case, most variation is coming from the arrival times from the customers, so that will be difficult to reduce. These are some of the effects we can detect in our simulation. Accumulation of WIP in front of a workstation due to insufficient staffing. Low capacity utilization due to excess staffing. Accumulation of WIP in front of the repair station, due to low first pass yield in test, N11. Accumulation of WIP in reception, Q4, due to arrivals above plan. High overall lead time, due to excess total WIP in the line. Test first pass yield below plan, which would create a bottleneck, both in the test and repair stations. Highly unbalanced line, as shown by large differences in capacity utilization. Proportion of products under warranty different to plan. This would require line rebalancing. Repair and functional test are the two operations which add value and consume most resources in the value stream, so we would expect to have high capacity utilization in both. When there is an increase in arrivals, we would expect a queue to form, causing an increase in the overall lead time. We don't want other steps, which require low staffing, to become a bottleneck for the line, so with a small increase in the staffing of those steps, which have high capacity utilization, we can make sure they never become the bottleneck. These small increases have increased the overall staffing by 1 person, and in this way, we have reduced their capacity utilization. You can now see that their cycle has been reduced well below 5, the takt time. The result will be a reduction of the average overall lead time for the line. We can see the line performance a long time now. We want to know the effect of a drop in test first pass yield from the planned figure of 80% to 70%. The first thing we notice is a red alert in the repair and test cycle times. They are now above the takt time, defined by the average inter-arrival time in K3. This means these operations have become the bottleneck for the total value stream. Looking at the evolution, we see a WIP build up first in repair and later in test. In a situation like this, we would analyze the failing items to look for the root cause of their failures to correct it. But in the meantime, if we need to continue the process, we will need additional test and repair capacity, increased test and repair staffing. We have increased repair from 7.1 to 7.7 and test from 2.4 to 2.6 to achieve cycle times of 5. These are some conclusions.
A static value stream map is a good start to understand how the value stream behaves. Feedback loops such as test repair loops are an essential part of the value stream, so they should be included in the VSM. A snapshot of the WIP situation along the line may not be representative of the normal operation. If the WIP situation is not typical, the NVA calculation will not be correct. The VSM simulator provides a deeper understanding of the process behavior, and it enables what-if studies to optimize the process. Simulation helps us understand some of the failure mechanisms caused by variation so we can act on the root cause to make real improvements.
You can see this article in Polyhedrica blogspot.